everybody, the iLord Root here, and welcome to this first episode of Video Game Science, which is all about optimizing the opening of OpenTTD. It is also the fourth episode of our OpenTTD tutorial. And so, for those of you coming from that playlist, welcome back. You might remember in the first episode we actually ended up with a income of something like £114,000, which it turns out is a little bit on the low side. However, if you're not familiar with that game, OpenTTD is basically an open source implementation of Transport Tycoon by Chris Sawyer. If you grew up in the 90s, you might remember it being a very exciting game. I remember there being a demo that really impressed me as a kid. But if you aren't, you might have heard of Roller Coaster Tycoon. It's also by Chris Sawyer and uses a lot of the same elements in common. It's comparable to SimCity and City Skylines, but instead of building the city, you build the transport network, you build the traffic, and so in that sense the roles are reversed. And before we move on, there's one question which you may already have that's fairly trivial to answer, and the question is, if your time's valuable, do you go with trains or aircraft? And the answer to that's fairly easy to answer because aircraft require significantly less effort, and that's largely due to the fact that trains require a lot of infrastructure and therefore time to place it. If you compare that to aircraft, you only require two airports and the planes. But this sort of opens up another question that itself is worthy of study, which is whether it's possible to mess up aircraft. And we're going to find that out in this particular study. So why are we doing this? Well, I've really got two motivations, and the first one, I freely confess, is entirely selfish. I want to perform better in OpenTTD, and I think a lot of people do too. And so, in a lot of cases, you'll see people do analysis of this kind, but they won't go all the way. They might collect one or two samples. They won't do hypothesis testing, and it makes it difficult to really get a good answer to the question. In fact, there are guides out there that make recommendations that we'll talk about here in a bit that maybe could withstand some scrutiny. But I also want to make science relatable, and I think that this is an important thing because the fact of the matter is that a lot of topics that we see in science, as lay people, aren't that easy to digest. They're technical in nature. They're about things, like genetics or physics or things of that nature that we don't really have that good of an understanding of. However, video gaming is something that most of us have experience with, and OpenTTD actually lends itself pretty well to this, and in fact a lot of people do serious analysis on OpenTTD. And part of that is the fact that we can very easily take measurements. And so, with that out of the way, there's really two major questions I want to ask that could be split into a bunch of other questions. And the first is, what's the best way for us to get as much cash as possible in the first year? And we're mostly interested in profit. We'll define that here in a little bit. But also, depending on the circumstances, does that finding change? And we really need to think of this as a set of multiple questions because, for instance, if I start a new map, does the profit change? Do the rules change? If I play differently, does that change things? So we're going to divide this into really three major experiments. And the first question is, in 1935, what is the best approach? And there's a few reasons for this. First of all, it's because that's what I prefer to play in. It's basically the earliest you can get access to all of the vehicles and maybe have a decent selection, although you still don't have much of one. And my hypothesis in this case is that trains will do better. This is from personal experience, but personal experience is anecdotal. It doesn't really demonstrate all that much. It just gives us a reason to have a hunch. And we're defining this by way as annual profit in year one. So one reason that I even started doing this in the first place is you read a lot of guides. They will say that airplanes are the way to do it, but they're probably not written with 1935 in mind. And in my experience, airplanes don't really draw in nearly as much profit as they could. Of course, we need to look at another case because if the guides are saying this, maybe there is a good reason to think this. So we're also looking at 1975. Again, this is strongly suggested by guides, and we could go with 1950, but there's not, because that is the default starting year. However, there's not much different in terms of 1950 and 1935. You maybe get a new airplane, and that's about it. But you get lots of options in 1975. A lot of people like to play it. And then there's this third question. Is it better to have more vehicles, that is, a maximally sized fleet, than it is to maximize the carrying capacity? And the reason we ask this question is that even though you don't lose anything from having more capacity than you need, it does create delays in frequency of transport. And the idea is that if we can increase the frequency of transport, we increase the flow rate. And so this is important because you can't just take your income, divide it by the number of days in a year, and then figure out how much we're making in a day. I mean, you can do that, but it's not nearly that useful because of the fact that really vehicles generate income in bursts. It's discrete. And so the more of these bursts we have, the hypothesis is that the more income we'll get overall because we'll be able to get more trips out, and therefore it's better to maximize fleet size. Now that we've discussed all that, let's talk about some of the background that'll help us model this situation and even get to some experiments. And the first thing we need to talk about is how we're defining profit. We could include, for instance, the cost of the stations and the vehicles. I don't because these are one-time costs, and we're trying to figure out, basically, if we let things run over the next year, what is the minimum amount of profit we can make? So in this case, we have profit defined as the income minus all of the recurring costs, including the running cost for the vehicles R, the property maintenance M, and the loan interest L. And this one's really interesting because normally this would be pegged down at £6,000 a year. However, if you go into debt, it can actually be greater. So profit is annual, as we just mentioned, and the idea is if we don't upgrade our infrastructure at all, how much could we gain, minimally by just allowing the game to run? And the reason for this is that you often want to think in the worst case. In other words, how much money can I rely on coming in? You will ultimately get more. Um, as for the data collection, it's more difficult to do it by vehicle, for instance, to where you could project into the future. I'd have to actually write a logging script to do that. And it makes the analysis a little bit more difficult as well. But that's something I may approach in a future episode. Now, as far as predicting income, it sort of goes without saying that our income is the sum of the income from all of the vehicles running, and you can see that at the bottom there with that thing that looks like an E. It's called the summation operator. We're basically saying that the total annual income is the sum of each individual vehicle's incomes. And what about the individual vehicle's income? Well, if we have income per unit cargo, I sub C, and the capacity of the vehicle, C sub V, and then the number of trips we're able to take in a year, T, and we can multiply them all together and predict the vehicle's income for the year. And it sort of goes without saying that we can actually figure out how many trips need to be taken in order to account for this. If we use just a little bit of algebra, then we can also take the income of the larger vehicle, divide by the capacity of this vehicle, and get the something proportional rather to the number of trips that need to be taken. You also technically need to divide by the income of each cargo unit, but we'll get something proportional. That's easy enough to correct. So the idea here then is that you might have something cheap and fast enough to totally replace one large vehicle. And this means that if we take another thing into consideration, we might be able to do more with it. So, for instance, distance is actually a pretty big deal in OpenTTD. And you often find yourself trading off distance between stations to timeliness. Because the greater distance you take cargo, the more you get paid for it. But cargo loses its value after a while. The longer it's out there, the lower it goes. And it's a non-linear relationship. So long routes not only decrease throughput, but they might also decrease profit. And I mention this because we're going to try to avoid two things in this particular experiment. Excessively long routes between stations. We especially want a route that can be completed within the year. And also excessively short routes, because if you have excessively short routes, you're not really getting much on that distance factor, and so you're significantly reducing your profit margin. So this leads now into our methodology. And it's worth mentioning that aircraft and trains are intrinsically different. Aircraft can only load a few kinds of cargo, which include passengers, mail, goods, and valuables. They only have a single size to choose from. But in terms of infrastructure, you only require the airports and the aircraft. They're also probably the fastest vehicles in the game. And finally, they have limited capacity. Now, trains, on the other hand, can transport anything, and they can be a variable size. This is going to actually factor into how we design our experiment. But they also require additional infrastructure, and that means that they have, some overhead associated with them. Compared to airplanes, they're quite slow, and to other types, they may be of a medium speed or slow speed, but they make up for it in their capacity. So these are things that aren't going to change between each of the two data collection phases that we're going to do. First of all, we're going to send aircraft out with mostly passengers and mail, and that's because it's the most available cargo and it doesn't rely on a secondary industry. Trains will transport coal for the same reason, and also because they get the best bang to buck here. As far as ships and road vehicles, we're not considering them because even though ships have good capacity, they take months sometimes. It might even take more than the year. Road vehicles are, maybe on par with trains, but their capacity is not good, so we're not going to consider them either. And then we're going to take out the full 300 pound or 300,000 pound loan, and we're not going to try to pay it off. It's possible potentially to pay it off, depending on how you play, but it's maybe closer to the worst case scenario to not do that, so we're not going to try to pay it off immediately. And then finally, we're going to pause whenever it's practical, so that we account for human error that can happen. And otherwise, when we can, we'll run at full speed. That is at time warp. Um, and that means that there's some notable exceptions. When we're buying a new vehicle or placing a station, we want to have it running normal speed, Same when we're placing infrastructure. And it's worth noting right off the bat that if I don't stop time in a timely manner, there is a little bit of error that can come out of that. These are my generator settings. I'm using a 1024 by 1024 map using Terra Genesis flat terrain type, low number of towns, normal number of industries. Could be either a 1935, 1975, smoothness rather, medium rivers, medium sea level, and manual map edges. And important for reproducibility is I'm using version 12.2 of the game. Every single time we take a sample, we're going to generate a new map so that the map doesn't factor in to the general conclusion. Now, for airplanes, what we're going to do is we are going to immediately take out the entire loan, place two airports that are somewhere between 30 and 200 tiles away, based on the largest city that is available. And then we're going to buy as many planes as we can. And we're going to full load passengers at each endpoint and buy new airplanes as soon as we're affordable. And we're going to try to low bounce them between airports. One issue that we sort of have here is that if we are in 1935 and 1975, the small airport isn't available, which means that the initial amount of money available to us is not the same, and we're going to have to account for that. If we need to be able to fit an airport in, what we're going to try to do is we're going to try to take the path of least resistance to try to get it as close to the town center as we can. And this can in turn affect the initial size of the fleet. Alright, so I just wanted to show off, I guess, a sample of our methodology here. You can see the world generation results here, and we're just going to real quickly show how we're dealing with the airplanes. I'm going to pause the game right now. I'm going to pin this just so that it's around. I am going to immediately unpause, control click on borrow to get the entire sum. And then we're going to go to town directory, sort by population, descending. And here, it looks like we maybe have 2 or 3 cities that we can go with. Let's see. Narnley is 1600, and Little Barwood has that much as well. So we're going to basically throw down these airports as close to the city center as we could get them. In this case, I don't really have to delete anything. So I'm going to unpause, put that down. But actually, I want its hanger up as well. And you'll see why. And then the same here. There's maybe not as convenient. Oh, we can put that in there. But if I needed to like delete a little bit of road or raise the land a little bit, I would do that. I'm not doing that here because it fits just fine. We're also going to take this guy here. And now we need to pick our plane. Let's pretend, for instance, that I am... Ooh, I got the wrong one. Let me just go down here and pin that up. I wanted the hangar, not the station report. I'm going to open up new aircraft on both, and let's say we're optimizing for the capacity. I'm going to click on the vehicle that I want, and I'm going to pin those. And then we are going to, holding down control, I can have up to 9 of these vehicles. So what I'm going to do, so I'm going to control click and get me 5 of those, and then same for Narnley, going to get as many as we can, and we've maxed out our ability to put stuff in. Now that they've got shared orders, all I'm going to do is control click on the source airport, airport here in the destination. And since we've got shared orders, then that won't create any major problems. Everybody will have the same orders. We're going to do the same, except we're going to go the opposite way with aircraft 2. I'm going to make sure these are pinned, and then I'm going to dispatch these aircraft. Now, I'm going to go ahead and run time forward, and I'm going to be ready. The next one I want to low balance is here in Narnley. So I'm going to be ready to clone the aircraft if we get enough in the way of money to do so, which I believe it's about 30 grand, thereabout. We are going to wait to see if that happens. Although it looks like we may not. We might have picked something just a little bit too little distance to make much of an impact. But assuming we'd have the money, I would pause it. I would take it out of time warp. Yeah, there we go. I would take it out of time warp and I would clone the vehicle. As far as measuring the distance, I'd choose one tile on the airport and measure it to the corresponding tile here. So we have a distance of 66 in this case. Now for 1975, it is actually going to be slightly different, and I'll show you why. We're not going to run the full simulation here, but it turns out that, as mentioned in the slides, we don't have a small airport because that small airport is now obsolete. So instead, what we're going to do is we are going to go to the largest city here, and let's see, what is Ninningwell? Ninningwell is probably within range. This is probably going to be the closest we can get to fitting it in. Yeah, I think this will be it. We just want a fairly reasonable catchment area. And we're going to do pretty much the same over here. Now in this case, these two roads are in the way. So I am going to delete them. And I should be able to put that airport in there. And likewise, choose my aircraft. Which, in this case, I think if we're optimizing for capacity, would be the Darwin 300. You want to make sure that since we have many more options, that you pick the right one, of course. And then you can finally, clone these guys and do all the other stuff. Now for trains, we'll also take out the entire line, but we're going to connect as many power plants to coal as possible, as many coal plants rather to power as possible. You could share a power plant, but we're going to not share the coal. We are going to get as many in as we can before money runs out, and then we're going to try to add another station, another train here. One thing that sort of makes this difficult is that you can't immediately build trains, neither can you build the stations immediately. So this means that there's a lot more effort involved and that there will be fatigue that'll come into this as well. And in addition to that, we require 2 endpoints, which means that we're going to have 2 stations plus the track connecting them. That's 90 pounds for every segment of regular track and 127 pounds for electrified track. Trains can also be of variable length. In order to account for this, we'll include the following: the cost of the engine And then we're also going to include for the I guess the fleet size optimization, 3 coal cars, and for the I guess the capacity optimization, 13 coal cars. Each train gets with it 2 stations, 2 depots, and 100 tiles of track. Whether or not we use that is up to us. We're definitely going to use the 2 stations and 2 depots. We may use less or more than the 100 tiles of track. And then finally, we're going to use opportunistic station placement, which means if we've got clusters of coal mines, we're not going to try to reserve those for a feeder network. That probably wouldn't happen. Typically, we're going to try to shoot for between 50 and 100 tiles, but if it makes more sense, we might use a shorter or longer route. And this is because we might have to route through farmland. This might be done occasionally, but we'll try not to. Now in this case, however, when we're working with trains, it is a little bit different. I've gone ahead and preemptively done some prospecting and some setup. And you can see here that we've got 2 coal mines and a plant nearby. This guy is too close over here on the right because it's not within our distance of at least 30 tiles. So we're going to want to hook this guy up here. Now we're in 1975. I'm going to go with the maximum size here at first, just to sort of show you, because it requires electric rail, and this is the only one. We're going to have a length 7 track, and down here we're going to have another length 7 track. And I'm going to try my best to avoid steep turns, in which case I'll actually want to place the depot probably behind the station. In this case, there's farmland there which we are trying to avoid, so what we're going to do is we are going to unpause, bring this out just a little bit, and I'm going to try to pause while we're making decisions, and just to make sure we've got electrified track here, because that's important. In either case, we want to put down our depots, and maybe try to get reasonably close to these guys here. And that should be connected. I'm going to go to the depot here, and I'm going to construct my train now, which I believe in this case is an SH40 plus, let's see, where's coal hoppers? 7 or 13 coal hoppers. We have 1 too many, so we'll take that out. And to sort of prevent issues with this, we're going to take this guy here. We're going to give it its orders, which involves full loading at the station and unloading there, and start immediately. However, I'm going to leave up that other station here. Let's say we want to hook this guy into, we want to make a duplicate. Well, we can do that. And they can share that power station as a result. The way that I'm going to do that is I'm just going to put my station down. We're going to put the depot behind it. Maybe get this thing hooked up. And in order to do that, it'll be fairly straightforward. We'll just take the path of least resistance here. So those guys are going to connect. In this case, we have no option but to bridge. It's the cheapest option anyhow. And we want to be careful about that, because if we delete the water, it's actually going to be a much more severe penalty for us. So we'll just get these guys connected. Probably not the best turn I could do here, but just for the purposes of demonstration, I'll do this. I'm not going to share orders on this clone train. Instead, I'm going to delete them. And I'm going to give brand new orders, even if the destination is the same. Finally, we got this guy down here that will hook into the same station. And instead of using electrified rail, because now this is going to be the, I guess, the vehicle or the fleet size optimization, instead what we're going to do is we're going to place down a 2-tile station that allows up to 4 vehicles in it. And by not using electrified rail, we definitely increase the amount that we have available to us. Again, we're going to have to bridge this gap. But that's rather important. I'm thinking maybe the approach I want to take is I want to come down here to connect it up. Probably not a bad idea. We'll come up here. What is... Yeah, we can get a connection up there. If we just extend this over by 1 tile. And then finally, where is our vehicle depot? Right there. New vehicle, we're going to go with, I believe it was the S.H. Hendry. And we're going to get the vehicle up to capacity. And then clone as needed. So these were done in separate tests, but you can very easily see what we did there. So here are the vehicles which we are using, and we've really got 4 major categories. We have 1935 for both optimized capacity and optimized fleet size, and the same for 1975. And the reason for us doing this is because with optimized capacity, we want to basically get as many cars on a train as possible, or use the largest plane. And then if we have a little bit of leeway, then we'll optimize for cost and speed. Fleet size, on the other hand, we'll try to use smaller vehicles. And in this case, if again, we'll try to get near equal cost with them, and we'll optimize secondarily for capacity and speed. Obsolete vehicles will be exempt at this point as well. So if you have like a really old plane, and this is more for 1975, it won't be considered necessarily. And we also make a distinction here between the theoretical initial fleet size, that is how many we could buy if we can instantaneously put down everything, and the actual fleet size that we have. The initial fleet size is something that we're going to target, but actual fleet size is basically what we end the year with. So, if we take a look at our airplanes, our chosen exemplars are the Bakewell Cotswold LB3 for capacity. This is actually the largest plane you can get in 1935. It has a unit cost of about, 30 grand. The Samson U2, slightly less, has actually got an initial count of 10, not 9. But then in 1975, we also have the Darwin 300, which is the 747 analog. It's got a lot of capacity in it. And for the fleet size, we have the Bakewell Luckett LB8. As for trains, there's a lot of caveats here. But for capacity, we're going to go with the Genzu A4 plus 13 coal cars. For fleet size in 1935, we're going to go with the Cheney Jubilee plus 3 cars. And the fleet size vehicle is nearly two-thirds. It's more than two-thirds, actually less, but it has less capacity. In 1975, we're going to go with the SH40 and 13 cars, and this one's notably different because it's an electric vehicle, so it's going to incur greater costs. And then for the fleet size, we're going to use the SH Hendry 25 plus the 3 cars. And you can see here that as far as the capacity is concerned, it's actually a lot more expensive as a result. We've already talked about profit calculation, but it's worth repeating here that we're looking at income minus expenditures, and it only includes network operation, property maintenance, and loan servicing because it's an annual rate. And as far as what we're collecting, we're going to collect income, operating costs of both the vehicles, property maintenance, and money spent on servicing the loan. And then we're also going to collect distance. Now, it's worth pointing out that the kind of distance we are collecting here is not Euclidean distance, that is the square root of x squared plus y squared. It is basically the maximum between the maximum between I guess the two variables here. And that's just because it's easiest to measure it that way. Oops, pardon me. Now, as far as statistical significance is concerned, it's worth pointing out that it may be that none of the strategies are really that different from each other, and you can do whatever you want. In order to determine this, we will use statistical significance via hypothesis testing. We have a value called alpha, and our statistical test will give us something called a p-value. Now, the p-value is the probability that the observed results are at least as extreme as they would be under the null hypothesis, and in this case that means there's no significant difference. So when p is less than alpha, which in our case is 0.05, that means that the likelihood that it occurred under control conditions is small, and we could say the result is significantly different. However, our data, the test that we use for that depends on whether or not the data is normally distributed. And for that, we're going to use Shapiro-Wilks. Now, I think that this requires some explanation. The null hypothesis in Shapiro-Wilks is that the data is normally distributed. And so, in order to get around that, what's typically done is you actually say p is greater than 0.1. This also provides greater margin for something being non-normal. It's a little bit more conservative. For normally distributed data, we're going to use student's t-test. In the case of multiple data, we're going to use one-way ANOVA. And then for non-normal data, we're going to use Wilcoxon rank sum. And in the case where we have multiple groups, we're going to use Kruskal-Wallis. And then we're also going to do something called principal components analysis. And this basically allows us to see if we can separate all of the vehicles out into groups. If mathematically, based off of the variables that we've collected, we can predict that there are differences. It's something called dimensionality reduction, and we can only do it on numeric variables. But it also, including some of the things we've measured, it also includes things like predicted vehicle costs. And the basic idea is we're going to take these combination of variables, and the first principal component is going to explain most of the variance in the data. You take all of the remaining data, and you do the same thing, or all the remaining variance rather. Well, you can take principal component 1 and plot it against principal component 2, and if the variables show differences between all, like, I guess, clusters, then that means that the groups are different. And so now, the much awaited experimental results. I collected 40 samples in total, about 20 of each per year, 20 of each per vehicle type, and 20 of each per strategy. In other words, with every combination of the three, I collected 5 samples. Um, and I could do more. The planes, it would be easier to do, but trains require tons of effort, and this took a lot of time to do as it was. So let's take a look at our mean profit. Um, in terms of mean profit with aircraft, capacity yields the greatest profit. It is worth mentioning that in 1935, one of our fleet vehicles crashed, which is not so good. With trains, on the other hand, you typically get marginally more income or profit by optimizing the fleet. But you can see in 1935, it it makes a difference. In 1975, it barely makes a difference. As far as the loan repayment time, when you are optimizing capacity, then you will in 1935 repay your loan using airplanes in about 13 years. And on average, you can expect almost a century when optimizing the fleet. In 1975, we get way better numbers here, which is about 2 years for optimizing the capacity and about 4 for optimizing the fleet. Uh, with respect to trains, we get much closer to these numbers. So in 1935, you can expect to pay your loan off probably by year 3. Same with optimizing the fleet. And in 1975, it gets a little bit better. You usually are able to pay it off within 1.5 years, which is rather nice. Now, if we take the profit, divide every single vehicle by it, since all of our vehicles are the same except for distance in the case of trains, we get a rough idea of how much profit each vehicle brings in the year. And we can see that in 1935, our Bakewell LB3s bring in about £4,000 worth of profit versus the Samson U5s, which bring in about 2 grand, and in some cases not even that. As it turns out, and we'll discuss this a little bit later, it is actually possible to go bankrupt. I did it a couple of times using the Samson. For 1975, your profit margins go up by an order of magnitude. And so here you can see that you get, when optimizing capacity, the greatest profit per vehicle, and that's to be expected. But you also get the, greater with the fleet as well compared to in 1935, enough to where you'd be able to more than break even. With trains, optimizing capacity appears to be the best way to go on average versus optimizing the fleet. But then, same in 1975. In fact, optimizing capacity in 1975 does give you marginally better average profit per vehicle than planes, but it's not much. And so, what about distance or profit per distance? Well, it turns out that trains also do the best here, um, in pretty much all categories, and they get an early advantage compared to airplanes in 1935. But are these results statistically significant? Well, we could see in some cases they are. It turns out that comparing air and train in 1975 does not show a significant difference. The implication of that is that you could really go with either in 1975. However, in 1935, there's a big difference. You can see that our p-value is really low here, and it favors trains as a result. So in 1935, we want to use trains. Um, in this case, also capacity in air also makes a big difference, although it doesn't in trains. And finally, aircraft versus trains. The overall conclusion is that it favors trains. And then just to sort of see this, you can again see, using this ANOVA here, the data did turn out to be normally distributed, that we have a great deal of significance between aircraft in 1935 and everything else. And in fact, there's no other significant relationship that was found in the ANOVA. So this is taking everything into account. Now, as far as our PCA plot, remember how I said that if things could be separated on the basis of the variables that we had in our data, that we could use this PCA to determine that? Well, here you could tell that aircraft are in their own clusters. So you have 1935 aircraft distinct from 1975 aircraft here. Trains are, you could argue that they're kind of sort of separated, but not really. They're more one cluster, which means that trains generally fall within the same regime. And that means that if we take a look at the things that are responsible for that, you can see that income is actually the greatest contributor here. Cost is also, it's not as nearly as important as income, but it's the next biggest component, followed by property maintenance, which also goes up with trains. And as far as the variance, you can see the first principal component actually describes most of it, with the second principal component being pretty paltry, and the third one maybe having a little tiny sliver of the variance. So, what does this all mean? Well, first of all, for airplanes, if we use airplanes, we want to optimize capacity. In every single test that we did, capacity was important here. And that means that loading, even though it might be marginally quicker, it's not enough to justify having more planes initially in the fleet, which is kind of an interesting observation. You wouldn't necessarily send a 747, for instance, to a regional airport, not for hauling passengers anyway. But there's a secondary thing here, which is that planes are more viable in 1975 than they are in 1935. We've already established this from our significance testing, but in the case of the Sampson U-52, there are actually cases where if the distance isn't large enough, you lose money and you can bankrupt yourself within the first year. And that means that the Bakewell LB3, which is the capacity optimized plane in 1935, even though you can turn a profit, it's still not nearly as much as trains, and so trains are definitely the way to go in 1935. For trains, you sort of have the same thing going on, I guess, but it really doesn't matter versus capacity and fleet size. Although you do get a marginal improvement with increased fleet size. This is probably due to the fact that you can get more trips in a year, rather than the fact that if you were to divide the actual profit by the number of days in a year, that they're really making more. However, this really comes down to deciding which is better for you, which is easier for you to use. I like sizing the train up to the capacity, the initial capacity of the mines. However, that may turn out to really not do much. It does sort of help you get your stuff out quicker, and it can get greater cash flow. But you might end up making more, especially on long haul routes. And that means that optimizing the train length may only provide marginal gains as a result. As far as trains versus aircraft, we did come to the conclusion that trains are generally better than aircraft, but it depends. So in 1935, definitely you want to do trains versus aircraft. And that's because the income is just much more for trains, and even the most expensive trains are still cheaper than their aircraft counterparts in 1935. In 1975, you actually have a little bit of leeway there. There's no real significant difference between them. And so you could choose the one that favors your play style and really not lose out on much. As far as general conclusions, 1935 is definitely more sensitive to the choice that you make, respecting the vehicles you deploy, than in 1975. Um, and there are things that were difficult to account for, like distance. I did record it so that you might be able to do a regression on it, and more on that here in a bit. But really, you want to optimize capacity when it comes to planes. Um, get the biggest plane out to the runway, to what the runway could support, and this might actually change over time. As a result, we only looked at the first year, so maybe you could run a more profitable regional service as a result. As far as things that could have compounded the experiment, the first one is the inability for us to inability to rather to not control time warp. As far as things that may confound this experiment, there are several. The first is our inability to finally control time warp, and this is important because the funds are always changing. So if I don't trigger it immediately, then you could lose money, or you at the very least it could miss a window, the earliest window to get a new element of your fleet out. As far as judgment error is concerned, this is important to mention. Uh, I did a cursory sort of thing, but maybe I didn't pick the best in terms of which planes would be best or which trains would be best. So in order to do that, it's probably better maybe to use that model to get the best idea of what I should be optimizing for. And of course, we don't project it to the next year, and this is sort of important because you will invariably make more the next year if you're already in the positive. Um, but in this case, we're using another thing to consider. We're using Manhattan distance because it's simple, not because OpenTTD really likes it or uses it rather. Finally, we had an airplane crash. This is actually rather important because the fact that we had a plane crash actually ended up saving the company, which is really bizarre. You wouldn't think that would be the case, but apparently it was. And then, also I recorded this over a few days. I did a lot of data collection. Fatigue may have actually factored into maybe not perfect decision making that would have affected the experiment. So, as a final aside, I just want to mention I have made both the data and the script that I used to process this available. It's in a scripting language called R. Feel free to use the data for whatever you want. It's in the public domain. The R script is licensed under the GPL, and make whatever modifications you want to it. Just keep the license, please. And let me know what you think about this. Let me know if you like this or if you have any insights. Until then, this has been Dialoid Root, and I shall see you next time.